Okay, EP Physics, here we are again. In the last video, we talked about Ptolemy's system and how it was trying to explain these motions that we described in the sky, kind of complex motions, actually, I'll have to admit. And again, the details aren't so much the point, it's how we account for them. Now, to summarize very briefly, Ptolemy lived 150 AD. He's the culmination of a bunch of Greek thought on this. He believed that the Earth is motionless in the center, and that all celestial motions were uniform and circular. He assumed it. He assumed all that. And you know what? I don't know, assuming, is that a good thing or a bad thing? Now, sometimes it's a bad thing when you make assumptions about people. You're just assuming that. Well, sometimes you have to assume things. The question is, are you assuming correct things? Will it play out? Will it pan out and hold up? Or will you be willing to change your assumptions if evidence shows that you might just be wrong? Now, Ptolemy had every right to make these assumptions. They were kind of reasonable, I would say. Do you feel like the Earth's moving? No, it doesn't feel like the Earth's moving. Motions look circular. Circles are perfect. Why not? Uniform? Why would they be otherwise? But then you saw how he ran into problems. And very briefly, he ran into the problem of retrograde motion, where he had to explain it with that teacup ride thing called the, see if you can think of it, epicycle. He used epicycles, a little wheel on a wheel. He also ran into the problem that I believe I talked about the seasons being different length. I think I got to that. I'll assume I did, but I'll briefly recap. He thought, like, say, the sun is going around the Earth, rather. He has the Earth in the middle, and the seasons would have been equal length, if the Earth were exactly in the middle, but the seasons aren't equal length. In fact, the time from the March solstice through to the March equinox through to the September equinox is actually longer than the other half of the year. So he had to account for this by putting the Earth a little bit off center. Well, it kind of fixes things. It makes these two seasons longer than these two seasons. But you know what? He assumed the Earth was in the center, and now he's not going to say it's in the center. If you challenged him on it and said, I thought you said the Earth was in the center, he'd go like, well, almost. I'm not sure I like, well, almost as an answer. It's kind of plain fast and loose with his assumptions. And then the assumption that the speed was uniform. This, again, is supposed to be the sun or some planet going around the Earth, which is supposed to be in the center. And in the case of the sun, it was found that it went faster over here and slower over here. And it's not supposed to. He assumed that the speeds are constant. So what you going to do? Well, what he did is he went to his happy place. I think we all wish we had a happy place right now. But anyway, his happy place was a place where nobody lives, right there, called the equant. And by the way, the Earth being off center, you might recall, is called an eccentric, because eccentric means off center. Like if you have some eccentric relative, they're a little off center. But in any case, this place is called the equant, and it's the place that equalizes the apparent speed and makes the sun look like it's going at constant speed. See, if you stand over closer to where it's going slower, that kind of makes that look faster, and you're further from where it goes faster, that makes it look slower. If you get just the right spot, Goldilocks, three bears, just right. If you get in just the right spot, you can live the happy illusion that the speed is constant. Now, I'm not trying to make fun of Ptolemy like he's just deluding himself with these little happy place things. Rather, it's actually a mathematical device. I'm not going to get into any computations involving this, but I tell you, it was a way of computing things. And you know what? It worked. Because models are supposed to do various things. What should a model do? Well, it should make sense of the observations. It should be a way to kind of put it all together, to encapsulate it all, so you don't have to just memorize the gazillion different factoids. Instead, you have this consistent, coherent picture that kind of like everything flows from it. You would like it to be fairly simple if you could. You don't want any more starting assumptions. I mean, if nothing else, because it gets complicated. It's hard to keep track of. There's this belief that it's very debatable philosophically. We don't really know. It's called Occam's razor. William of Occam was some thinker way back England somewhere, many hundreds of years ago. And he proposed that if you had multiple explanations for the same thing, that you should, and they both work, you should use the one that's simplest. And simplest usually means with the fewest assumptions. Instead of assuming 12 different things, maybe one model assumes 12 different random, can't proven things, and maybe works. And another model only assumes 3 things. Go with the one with 3 things. The ones with lots of assumption are called conspiracy theories, and you know where that can go sometimes. Of course, there's such a thing as a conspiracy. We can't prove that models should be simple, but we feel like they ought to be, and I'm going to go with the easy one. In any case, his model started with simple assumptions. I need to say one more thing about models, 2 more things. One is they need to make predictions. They need to successfully predict stuff. Like, what's a model like this supposed to do? It's supposed to predict where a celestial body is going to be in the sky. You might have some reason you want to know. Maybe it's for calendar purposes. Maybe you're an astrologer and you care. Or maybe you just inquiring minds want to know. So if you can predict where something's going to be, that's a big check mark in the box for a model. Another thing we're going to see models should do, is be full of surprises, good surprises. Order now and you also get for 3 easy payments of $19.95 more than you bargained for or expected. In any case, Ptolemy's system stood the test of time, partly because it worked and partly because of the times. Ptolemy lived in 150 AD in the Roman Empire. Things went okay for a while after that. And then within a few hundred years, the barbarians are storming the gates of Rome, and as civilization's going to decay, they're drinking out of lead goblets and going crazy or something. Or maybe they got all decadent, and I'm not sure what all happened to lead to the fall of the Roman Empire. But the civilized world kind of went down. And there were other things to think about besides stuff like this. You're looking for food and trying not to get killed. You don't worry a whole lot about where little planetary bodies are in the sky. To fill in a few hundred years of history very briefly, the expansion in the Arab world, the Moors coming across North Africa and up into Spain. First, they conquered a bunch of stuff and kind of made a mess on the way, but they did get books out of the Library of Alexandria, and some of them, once they settled down and had places like Cordoba in Spain and Damascus, Syria, and Baghdad, Iraq, they settled down and they did science for a while. And they learned this stuff, and they named a lot of the stars. A lot of them have Arabic names. But they didn't fundamentally transform it. They didn't come up with any big revolutionary changes. They tweaked things, messed with stuff, debated whether they liked equants or epicycles or eccentrics more, but they didn't fundamentally overhaul it. Instead, in 1492, cuando Fernando y Isabel, los reyes católicos, expulsaron a los moros de España, 1492. Okay, that's Spanish for Ferdinand and Isabel drove the Moors out of Spain in 1492 after like a 700-year reconquest of Spain. And when they did that, they found these libraries that the Moors had, like in Cordoba, with ancient knowledge in them, treasured ancient knowledge. And bored monks in France and Germany suddenly had new reading material. They got down there, got the stuff, went back and studied it and liked it. And, you've probably heard about, and for good reasons, you've heard about conflicts between science and religion sometimes. I can tell you things were going pretty well then. A guy named Thomas Aquinas, a French monk, put together the Ptolemaic system with Catholicism and came up with this synthesis, this grand synthesis where, I just forgot the name of it. Anyway, it'll probably pop in my head in a minute. But put it all together. And so as the Renaissance gets going, as you pull out of the Middle Ages in Europe and say, get through with some of the plagues, in say 1400s with the universities in Europe, when you learned about astronomy, you learned that the universe was this encapsulated thing with the earth in the center, and you learned that heaven was out here, and it all fit. I'm sort of pseudo-cultured in that I know what I'm supposed to have read to be cultured, but honestly haven't read it. I have not read Dante's Inferno, but I know about it. And I know that Dante's Inferno, maybe some course they make you read that at Woodward, involves these layers of heaven and hell. Guess where Dante got the idea? They are straight out of the Ptolemaic cosmic model, where these concentric shells happen, So anyway, Catholic Church loved it. They thought the earth was round. They thought the earth was in the center. And guess what? We're in the center. Yeah, mankind got to be right in the middle of everything. So it all made sense. It was all good. Scholasticism, that was the name of it. That's the name of it. Scholasticism, this melding of science and religion. In any case, they start learning the Ptolemaic system, and people are pretty impressed with it. They also learned Aristotelian physics. You remember the stuff about how heavy things are supposed to fall faster, and they want to, go be with their friends on the ground, and air bubbles go up through water because they belong in the air. All that was ancient knowledge resurrected and taught in European universities at that time. So anyway, who I want to introduce you to that comes into this world in the 1400s, I think he was born in 1473, is Nicholas Copernicus. That's his Latinized name, Nikolai Kopernik. He lived in what is now Poland, and he was a Catholic Church official, the canon of the Cathedral of Frauenburg, I believe. So he was also Nick of all trades. Nicholas. He was a Renaissance man. Yeah, Renaissance. Did all kind of stuff. He was a lawyer, judge, church official, a doctor, meaning, he'd probably cut you and bleed you if you were sick, that kind of thing. But he was also an astronomer. And it was a little bit of a side thing at first, but boy, it sure got to be what he was known for. He had a pet peeve. That thing I talked about a little bit ago, those equants, the happy place, he thought, oh, come on now. That's cheating. See, Ptolemy cheated in a couple ways on his own assumptions. First, he said the Earth is in the center, and then with an eccentric, it's a little off center. And then he said that things went at a constant speed, and they said, well, they don't really, but they would look like they would if you lived over here at the equant. Copernicus saw right through that, and he vowed to rid the Ptolemaic system of equants. I'm going to make a rough analogy. Not that these two people were friends, but in fact, they weren't. But Martin Luther, about the same time, was going to try to reform the Catholic Church, indulgences and stuff like that they were selling. He was going to try to straighten some of that up, the 95 Theses and all that. And oops, he started a whole revolution, a whole reformation, and a big split. Copernicus only meant to tidy up the Ptolemaic system, and as you see where this is going, he ended up overthrowing it. But at first, he just didn't want equants. So he got to reading a lot, and in reading all kind of ancient stuff, he ran across this weird idea that some ancient Greeks who kind of died and nobody listened to them. I guess somebody wrote it down and it survived, but I hardly had any followers. Thought the sun was in the center, and that the earth went around the sun, and that the earth spun on its own axis. That's familiar, isn't it? Might have learned that in 3rd grade. Yeah. Some ancient people thought it. You could say they're way ahead of their time. But again, hardly anybody listened. It was hard to believe that the earth would be moving and everything. So the geocentric, earth-centered thing triumphed for almost 2,000 years. And here comes Copernicus, runs across this idea, and first probably he thinks you gotta be kidding. How could the earth be moving? But I guess he slept on it. Might even have bad dreams about it. I don't know. Had a revelation. I don't know. But somehow Copernicus decided that maybe things would work out better if you put the sun in the center and let the Earth go around the sun and let the Earth spin on its own axis. I got to distinguish between two words here. There's rotate and revolve. And they are not the same thing, and people mix them up all the time. Which one is this? Well, I can't hear you. Rotate. Revolve is when you get up and actually go around something else. So the Earth rotates on its own axis while, let's say it this way, while revolving around the sun. Does both. He didn't just pick one. You could have said it did one and not the other, but no, he says the Earth does two motions. It spins on an axis, the axis through the North and South Pole, of course, and it revolves around the sun. How long does it take to spin on its own axis? He says the Earth takes 23 hours and 56 minutes. Now, you might have thought it was supposed to be 24. Close. You've already learned, I think we already said, that with the Ptolemaic model, the star sphere spun around the Earth once every 23 hours and 56 minutes, and the sun was creeping backwards, like somebody going back to the bathroom on the back of the speeding bus. You know, that's an analogy. I think I used it with somebody. But anyway, Copernicus says the Earth spins once every 23 hours and 56 minutes. So the stars zip around every 23 hours and 56 minutes. You see a star at 8 o'clock one night. The next night it's there at 7:56. The next night 7:52, and so on, which adds up to a day in the course of a year. They're back where they start all over. Now, in terms of how this relates to the revolution, see, the revolution is 1 year for the Earth to revolve around the sun. That's what a year is, and I think you probably knew that. I don't have enough room here to act everything out quite like I want to, but I'll try. So, say the Earth starts here, and you look at the sun that day, and the sun's out there and some stars way out here. I'm going to kind of exaggerate. It's not going to really move this far in a day, but what if it moved to here in a day? Then to look at the star, which is, I'm sorry, the star is terribly far away, so I should have just drawn a line like this. Do you see that the Earth would have to turn a little bit more to get the sun to be in the same part of the sky? It has to turn for an extra 4 minutes. I won't belabor that, make a big deal of it, but basically the Earth is supposed to be doing both these things. What does it explain? First of all, if the Earth rotates on its own axis, just like that, you've explained all the celestial daily motions. You've explained why the stars and the sun and the moon and the planets all zip westward across the sky. They appear to zip westward because we are rotating eastward. And you probably have heard that before. Some of you might have already understood it, might have thought about it when we brought it up anyway. Yeah, that's why the sun rises in the east, because the Earth's rotating towards the east, and it makes the sun appear to go across the sky toward the west. Obviously, there are two reasons the room could be spinning around me. It could be spinning around me because it's really spinning around me, or I could be spinning and it makes the room look like it's spinning around me. Or I could just be dizzy. I don't know. In any case, we've got all the daily motions taken care of just like that if the Earth just rotates once a day. How about the year thing? Remember how we see different constellations at night? Certain time of night, different times of year. I go out in the winter, and I see Orion in the south in the evening while I'm walking the dog. Well, by summer, I don't see Orion anymore. I see Sagittarius or Scorpius or something in the south when I go out and walk the dog in the evening. Why? Easy for Copernicus. Let's say that this star is maybe a star in Orion. When the Earth is over here, you see, this is the night side of the Earth, and this is the day side of the Earth. So here's a person at night. It's a very tall person. This person at night is looking up in the sky at Orion at night in the winter. Come summer, when it's over here, night's on this side now. And now, it's not that Orion doesn't exist anymore. It does. It's over on the other side of the sun. But instead, you're going to see these stars at night. Clearly, the stars you see at night are the ones that are on the other side, away from the sun. And if you go around the sun once a year, you're going to see the stars go through this pattern once a year. And it's going to look like the sun went around you once a year, eastward, along the ecliptic, just like we described before. So we've just explained the daily motions. We've explained the annual motion of the sun, at least. We didn't mention other things yet. Got those two down, though. What about other stuff? What about the seasons? Now, you might have seen, I didn't make a big deal of it, but I did show at some point, I hope. At least, hey, listen, you know what? If I miss something in these videos because I just overlook it, astrohandout.pdf, pretty much got it all. So be sure you read that. Anyway, you know, the Earth's axis is tilted 23.5 degrees. You know what I got? I had one at home. I'll get it. A globe. Upside down. Okay, it's a globe. Sorry that part of the Philippines and Borneo has been ripped off the Earth. I hope that never really happens. But you see that it's got this, it can spin on its axis, so that's how the Earth rotates. And then if I'm the sun, it also goes around me, way out of scale here. The distance, I mean, the Earth is puny compared to the distance to the sun. Now what's missing here that did break? Yep, it broke. This is my one that I was supposed to throw it out, I think, and I didn't. But it didn't. It's broken down here, but it used to have a mount that it went on, so it was supposed to go about like this. And you see when it spins, there's a tilt. So when the Earth goes around the sun, it's got this tilt to the axis. Let me show you how that makes summer and winter. First of all, let me tell you what does not make summer and winter. The Earth is closest to the sun on, guess what date? January 3rd. And it's furthest from the sun. Oh, here's my doggy. It's furthest from the sun on July 4th. That sounds all backwards. It just sounds wrong. I mean, July's hot. Why is July hot if we're furthest from the sun then? Well, first of all, our distance from the sun only varies just a little bit, and it's not enough to make seasons anyway. What makes the seasons? Watch this. Okay, so here's the Earth. Here's the North Pole. And I'm going to be the sun. Again, the distance is way off here. But as the Earth rotates like this, look at this. Wow, look. In the U.S., that's the U.S. there, I'm like almost overhead. Not only that, I can see the U.S. for most of an Earth rotation. And they can see me. It's up like, 14 hours a day or more. If the sun's up for 14 hours and it gets up high in the sky where the rays beat almost straight down, it's warm. Oh my God, look at the North Pole. I can see the North Pole the whole time. 6 straight months, the North Pole gets to see me. South Pole, I don't see it all. It must be cold down there. Ooh, look, down in Argentina or Australia there, it's winter. They don't get a good look at me, and I'm not up very much. Wait 6 months, and it's over here. Now it's the southern hemisphere's turn to bask in my bounteous rays. You see, I'm shining almost straight down on Australia now, and they get to see me a lot. And these people up here hardly get to see me. Well, a little bit, but not much. And it's winter up there. That tilt explains the seasons. That's pretty much how Copernicus said it. With some technical, small detail different. Okay, but anyway, I would say all we've done is we've replaced one object's motion with another object's motion. And notice that all these things we just explained, Ptolemy had explained them anyway. So why do anything new here? All right, I'm going to tell you, if I had to sell you on Copernicus' system, this would be my #1 selling point. It might be my only really big selling point. Here it comes. Retrograde. Retrograde's weird. Ptolemy handled it. He had those epicycles, They work. But how's Copernicus going to handle this? Also, Ptolemy's epicycle was all conspiratorial. It had two different kind of rules, one thing for Venus and Mercury, a different kind for Mars, Jupiter, and Saturn. What we're going to do now is say how Copernicus handled it. I wish I had a bigger board here. I draw as best I can. Here's how it goes. Here's the sun. Let's say why Mars retrogrades. Here goes the Earth around the sun. Sorry, it's not a very good circle. Yuck. It's not exactly a circle. Anyway, there's the Earth going around the sun. Here it is at one point, and here it is like every month as it goes around the sun. Mars is also going around the sun. Maybe Mars is over here at some point. And maybe you look at Mars from the Earth, and it appears to be over there. Now, Earth is going this way, and Copernicus says Mars is going the same way, but slower. So next month, the Earth is there, and Mars hadn't moved quite as much. But you see that Mars, apparently, as seen from the Earth, has moved that way, as seen against the background of distant stars. Next day, month, Earth is here, Mars is here. Ooh, it's moved a little bit, maybe. Next time, next month, here's Earth, here's Mars. Whoa, look at that. Look at this, Earth next month, Mars next month. It's going backwards. And here's Earth, and here's Mars. And man, it's starting to go forwards again. I've just shown you with this little weird drawing that Earth passing Mars makes Mars look like it goes backwards for a little bit. Of course it does. You know, when you're going down the road in a car and you're going to pass another car. At first, the car looked like it was going forwards. Right at the moment you pass it, don't look while you're driving. You're the passenger. You look out there and the car may look like it goes backwards for a very, very simple reason. You're going faster than it is and you passed it. That's all it is. According to Copernicus, that's all retrograde is. We just pass a planet and it makes it look like it's going backwards. Get it? It doesn't actually turn around and go backwards. And I didn't even need an epicycle to make it go backwards. And there's more. Remember the thing about how Ptolemy was all happy because his model predicted planets would be brighter while they're retrograding because his loop-de-loop teacup things would be closer to the Earth at that time? Can Copernicus match it? You betcha. Yes. While it's retrograding, it's closest. Of course it is. You ever notice like a car that you're passing looks biggest while it's going backwards? Of course it does because you're passing it. You're close to it. But there's more. Copernicus can also explain something Ptolemy couldn't. Ptolemy had no idea why Jupiter or Mars, say, would retrograde when it was opposite in the sky from the sun. It just did. Just the way it is. Not very satisfying. However, Copernicus has a beautiful explanation. Of course, Mars appears to be in the other direction from the sun when it's retrograding, because that's when we're cutting in between it and the sun. So simple. No conspiracy needed. And there's more. Remember how Venus and Mercury made a different kind of rule where they always appear to be really close to the sun in the sky? Guess what? He says Mercury and Venus appear to be close to the sun in the sky all the time because they are close to the sun. Yep. And why would there be two planets that did one thing and three that do the other? Because we happen to be the third one out. If there are two in between us and the sun and more out there, you're going to have different rules. It's because we're the third one. God, it's so simple. That is the biggest selling point for Copernicus right there. But I'm going to have to undermine him a little bit in a couple of ways. Okay, so retrograde's great. No epicycles needed for that, at least not at this point. But let's see some problems with Copernicus. Now, some of it is simply that his employer, the Catholic Church, had already decided the Earth is in the center because Thomas Aquinas said Ptolemy's really neat. And because we fit in the center, we're the most important things, we ought to be in the center. Kind of hurts to be kicked out of the center. You know, little kids who or bratty, you say, you think the whole world revolves around you. Get it? We, collectively, humanity, thought the whole world revolved around us. You take geocentric, and you all you got to do is switch the E and the G. You get egocentric. They kind of go together. But it was way more than that. It wasn't just feelings. It was also that physics itself, Aristotelian physics, involved the Earth being in the center, and the rocks fall to go be with it. That was the explanation of everything. And if you throw out the Ptolemaic system and go for this, you're going to have to throw out all of known physics, basically. It's a high price to pay. It's called throwing the baby out with the bathwater. I don't know if you know sayings like that or not. Now, there's a little bit more I'm going to say here about Copernicus. Another thing is there was another problem. I'll try to explain it fairly quickly. So I'm going to kind of run along on this one. Okay, if Copernicus were right that the Earth moves around the sun, if that's true. Now, by the way, if the Earth moves and there's like air everywhere, you have this horrific wind blowing on you all the time. So one thing you got to believe Copernicus is got to believe in a vacuum. And nobody believed in a vacuum. They thought matter had to fill all of space. That's another. But let me get to this thing. I want to talk for just a moment about something called stellar parallax. Okay, stellar means of the stars. Parallax is like this. When you move, you can't tell what I'm looking at. I'm looking at those thing that plants hang from out there. Anyway, so when I move this way, and I'm going to let you see it. Watch parallax. You're about to see parallax right here. Watch. See that thing out there? See how everything shifts when you move? You see things appear to move against the background, and I dropped my marker. I'm going to get it back somewhere. You see things move against the background like that? That's parallax, and a shift in something else's position, apparently due to your motion. Now, if the Earth moves around the sun, and there are distant stars out here, the star ought to appear in a different direction depending on what time of year it is. You ought to see the star shift back and forth because of us moving. If you think about it, retrograde kind of is a parallax effect, but the stars ought to do it too. And people looked. I guess Copernicus probably looked. And you know what? Oops, they didn't do it. Nobody could see the slightest shift of the stars. The easiest explanation for that is that we're not moving. I could say, why isn't that thing shifting back and forth for me right now? And you could say, because you're not moving. But what if I am moving? Is there any way you can explain it not shifting back and forth? Yeah, maybe you'll think of it. Could be really, really, really far away. Because when I go outside and look at the moon in the sky and shift my head back and forth, I don't see it like go in front of different stars because it's so far away. So Copernicus' only lame excuse for a lack of seeing parallax is that the stars are so absurdly far away that you just can't see it. Good explanation, except it's also way too easy to say. If I have a theory that these little things called smagoons are running around on this piece of paper right now, and you say, yeah, where are they? I say, well, they're there. You say, well, I don't see them. And I say, like, oh, yeah, they're too small to see. I mean, it's too easy to say, right? For Copernicus to just declare that the stars are absurdly far away and that's why they don't shift back and forth, it's just too easy. Might not be wrong. It's not wrong. He's completely right, it turns out. Like 300 years later, we found out. But people didn't see it, so they couldn't believe it. That's an argument against Copernicus' system. I'll wrap it up by saying this. Copernicus had some pretty bright ideas. He explained retrograde beautifully. He's got alternate explanations to Ptolemy's system, but you know what? It didn't work any better. It didn't make any better predictions. It did make things simpler in some ways, but it also conflicted with other things and even with religion at the time. Awkward for him being a Catholic Church official. And so it didn't go over real well. And it took like 100-ish years after Copernicus before people started really believing. He was handed the first copy of his book, The Revolution of a Celestium something, on his deathbed. Yay, they finally published it. And kind of a disclaimer somebody else wrote in the front to kind of get it past the censors or undermine it. I don't know. Anyway, done with Copernicus for today. I know that was a long video. Thanks for listening. I'll post some questions. Please also read astrohandout.pdf. Bye.